Hi, this is chemical quantities, or otherwise known as mole calculations. You'll have to be able to do a variety of calculations relative to moles, from converting from moles to mass, mass to moles, moles to the number of particles, and so forth. Let's get started. Every year, contestants from all over the world travel to Harrison Hot Springs in British Columbia, Canada, to compete in the World Championship Sand Sculpture Contest. Each contestant creates a beautiful work of art out of millions of tiny grains of sand. You could measure the amount of sand in each sculpture by counting the grains of sand. But wouldn't it be much easier to simply weigh the sand? In this section, you'll discover how chemists measure the amount of substance by using a unit called a mole. And I'm going to say this more than once. The mass in grams of 1 mole is equivalent to the mass of 1 particle in atomic mass units. And that's a fact. All right, here's a sand sculpture. Let me say that again. The mass in grams of 1 mole of any particle is equivalent to the mass of 1 particle in AMU. Okay. Sodium has an atomic mass unit of 23. So a mole of sodium would be 23 grams. Water, H2O, hydrogen is 1, oxygen is 16, 2 hydrogens, 1 oxygen. A mole would be 18 grams. You live in a quantitative world. The grade you got in your last exam, the number of times you heard your favorite song on the radio yesterday, and the cost of a bicycle you would like to own are all important quantities to you. These are quantities that answer the question such as how much or how many. Scientists answer similar questions. How many kilograms of iron can be obtained from 100 kilograms of iron ore? How many grams of hydrogen and nitrogen must be combined to make 200 grams of the fertilizer ammonia? Questions like these illustrate that chemistry is a quantitative science. A quantitative science. In your study of chemistry, you will analyze the composition of samples of matter and perform chemical calculations that relate quantities of reactants in chemical reaction to quantities of product. To solve these and other problems, you will have to be able to measure the amount of matter you have. How do you measure matter? One way is to count how many of something you have. For example, you can count the CDs in your collection or the number of pins you knock down when bowling. Another way is to measure matter is to determine its mass, or count the number of DVDs in your collection, or count the number of computers in your collection, or count the number of phones you have. These are all ways of measuring matter. We will understand the mole. A mole is simply a count. It's a number, like a dozen eggs is 12. You can buy potatoes by the kilogram or pound, and gold by the gram or the ounce. You can also measure matter by volume. For instance, people buy gasoline by the liter or the gallon, and take cough medicine by the millimeter or the teaspoon. You often measure the amount of something by one of 3 different methods: by count, by mass, or by volume. For example, you can buy soda by a 6-pack or by the liter. Figure 1 on the next slide shows you how you might measure the amount of grapes you buy. Again, the mass in grams of 1 mole of any particle is equivalent to the mass of 1 particle in AMU. Okay, methane. 12 is oxygen, and 1 is hydrogen, 4 hydrogens, 1 carbon. So it's going to be 16 AMUs. The mass of 1 mole will be 16 grams. A grocer's scale measures the weight of the grapes you buy. 1 mole has 6.02 times 10 to the 23rd particles. always. Here are examples of the grocer's scale. The grocer's scale will measure matter by weight. Now, in the United States, we use pounds. In England, you can use pounds or stones, depending on what it is you're weighing. A person in England is weighed in stones. Some of the units used for measuring indicate a specific number of items. For example, a pair always means two. A pair of shoes is 2 shoes. A pair of aces is 2 aces. Similarly, a dozen always means 12. A dozen eggs is 12 eggs, and a dozen pens is 12 pens. Apples are measured in 3 different ways. At a fruit stand, they are often sold by the count, 3 for $2.40. In a supermarket, you can usually buy apples by weight, $1.29 a pound, or mass, $2.79 a kilogram. At an orchard, you can buy apples by volume, $12 a bushel. Each of these different ways to measure apples can be equated to a dozen apples. By count, 1 dozen apples equals 12 apples. For average-sized apples, the following approximations can be used. By mass, 1 dozen apples equals 2 kilogram apples. By volume, 1 dozen apples equals 0.2 bushels of apples. Figure 2 on the next slide shows other items sold by count, weight, and volume. Knowing how the count, mass, and volume of apples relate to a dozen apples allows you to convert among these units. And remember, the mass in grams of 1 mole of any particle is equivalent to the mass of 1 particle in atomic mass units. Water is 18 atomic mass units, therefore it would be 18 grams for 1 mole. You can buy items by different types of measurements, such as a count, a mass, a weight, a volume, classifying which of these common items are being sold by weight, by volume, by count. So, if I had a particle such as sodium chloride, I add it up and I find it's 58 atomic mass units. Well, that's the mass of 1 mole of sodium chloride. Here is birdseed. It's sold by a bag, okay, that is dry weight. You can see down in the lower right-hand corner. You have volumes of paint. You have count of screws. So there's different ways of buying things and packaging things, etc. For example, based on unit relationships given above, you could calculate the mass of a bushel of apples or a mass of 90 average size apples using conversion factors such as the following: 1 dozen apples over 12 apples, 2 kilograms of apples over 1 dozen apples, 1 dozen apples over 0.2 bushel apples. What are 3 ways of measuring the amount of a substance? Well, we just looked at it. We said mass, volume, or count. Counting objects as big as apples is a responsible way to count the amount of apples. But imagine trying to count the grains of sand in a sand sculpture. That would be an endless job. Recall that matter is composed of atoms, molecules, and ions. These particles are much smaller than grains of sand, and an extremely large number of them are in even a smaller sample of the substance. Obviously, counting particles one by one is not practical. However, think about counting eggs. It's easier when the eggs are grouped into dozens. A dozen is a specified number. 12 things, 12 of things, 12 eggs is a dozen eggs. Other common groupings of items are shown in Figure 3 on the next slide. Chemists also use a unit that is a specified number of particles. The unit is called a mole. Just as a dozen eggs is 12, a mole, MOL, of a substance is 6.02 times 10 to the 23rd representative particles of that substance, and is the SI unit for measuring the amount of a substance. The number of representative particles in a mole, 6.02 times 10 to the 23rd, is called Avogadro's number. It was named in honor of the Italian scientist Amedeo Avogadro, 1776 to 1856, who helped clarify the difference between atoms and molecules. Words other than mole are used to describe a number of things. For example, a ream of paper is 500 sheets. A gross of pencils is 144. That's 12 times 12, by the way. A dozen eggs is 12. So, how many other ways can you think of organizing matter? Are there many? Are there few? You have reams of paper, 500 sheet. You have a box, which has 10 reams. You have 500 sheets per ream. So how many, that's 5,000 sheets of paper that are organized in a box. When I load a printer, I will load a ream at a time. I will load 500 sheets at one time, a ream. Here is a gross of pencils. You have 12 pencils. You can see you have 6 pencils, and then underneath that there's 6. So there's 12 times 12 is 124, 144. Here's a dozen eggs. A dozen. What's the difference between a mole and a dozen? Well, the number in the count, but the fact that but they're both counts. So that's a way of organizing matter, and we do it with atoms and molecules and formula units. The term representative particle refers to the species present in a substance, usually atoms, molecules, or formula units. The representative particle of most elements is the atom. Iron is composed of iron atoms. Helium is composed of helium atoms. 7 elements, however, normally exist as diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The representative particle of these elements of all molecular compounds is the molecule. The molecular compounds water, H2O, and sulfur dioxide, SO2, are composed of H2O and SO2 molecules respectively. For ionic compounds such as calcium chloride, the representative particle, the formula unit, CaCl2. What did I just say? The formula unit. A molecule is molecular, a formula unit is ionic. Okay, converting number of atoms to moles. Magnesium is a light metal used in the manufacture of aircraft, automobile, wheels, tools, and garden furniture. How many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? So what do we know? We know the number of atoms, 1.25 times 10 to the 23rd. We know a mole of magnesium, 6.02 times 10 to the 23rd. We have the desired conversion, and we want to know the number of moles of magnesium. And here it is. The conversion factor, 1 mole over 6.02 times 10 to the 23rd atoms of magnesium. Multiplying atoms of magnesium by the conversion factor gives the answer. 1.25 times 10 to the 23rd times 1 mole over 6.02 times 10 to the 23rd atoms. I get 2.08 times 10 to the negative 1 moles of magnesium. Because the given number of atoms is less than 1/4 of Avogadro's number, the answer should be less than 1/4 moles of atoms. The answer should have 3 significant figures, 2 or 3. Remember, 1 mole equals 6.02 times 10 to the 23rd particles. The mass in grams of a mole is equivalent to the mass of 1 particle in atomic mass units. A mole of any substance contains Avogadro's number of representative particles, 6.02 times 10 to the 23rd, representative particles. Table 1 on the next slide summarizes the relationship between representative particles and moles of substances. Converting number of particles to moles, the relationship 1 mole equals 6.02 times 10 to the 23rd representative particles is the basis for a conversion factor that you can use to convert numbers of representative particles to moles. Moles equals representative particle times the ratio of 1 mole over 6.02 times 10 to the 23rd representative particles. This is representative particles of moles. You look at the number of particles in each mole. It's all the same, 6.02 times 10 to the 23rd. Here's the formula, the nitrogen atom, the nitrogen molecule, the water molecule. Look at the calcium ion, Ca plus 2. The chlorine, the calcium fluoride particle, CaF2, and sucrose. Converting moles to the number of particles. Converting moles to the number of particles. In this case, converting moles to number of atoms. Propane is used for cooking and heating. How many atoms are in 2.12 moles of propane? C3H8. C3H8. And there's some views of propane burning, propane gas burners. Number of moles we know, and that's 2.12 moles of propane. 1 mole propane equals 6.02 times 10 to the 23rd molecules of propane. 1 molecule of propane is 11 atoms, 3 carbon atoms and 8 hydrogen atoms. The desired conversion is moles to molecules, molecules to atoms, and then we want to know the unknowns, number of atoms. And the first conversion factor is 6.02 times 10 to the 23rd molecules of propane over 1 mole of propane. Second conversion is 11 atoms per 1 molecule of propane. So that's it. Essentially you're finding out, you're converting to the number of particles in 1 mole of propane, and then you're multiplying that by 11, the number of atoms in 1 mole. Because there are 11 atoms in each molecule of propane and more than 2 moles of propane, the answer should be more than 20 times Avogadro's number of propane molecules. The answer has 3 significant figures based on the 3 significant figures in the given measurement. Remember, when you make a conversion, you maintain the number of significant figures. So you're converting the moles to particles, and then you're converting from the particles of a molecule to the particles of an atom. Checkpoint. How many representative particles are in 1 mole? 6.02 times 10 to the 23rd. Converting moles to number of particles. Now suppose you want to determine how many atoms are in a mole of a compound. To do this, you must know how many atoms are in a representative particle of a compound. We did this in the sample problem. That sample problem, I guess, was put in the lecture a little early, but you can deal with it. This number is determined from the chemical formula. Figure 4 on the next slide illustrates this idea with marbles. Marbles are atoms. In cups, they're molecules. Okay? The cups are the molecules. The number of marbles in a dozen cups is 6 times 12. All right, so there's more than 6 in these particular molecules, but that's just the number of atoms. Just try to make a point. Figure 4 on the next slide. A dozen cups of marbles contain more than a dozen marbles. Similarly, a mole of molecules contains more than a mole of atoms. How many atoms are in 1 mole of molecules in each molecule if each molecule consists of 6 or more atoms? Again, you convert to the number of particles in 1 mole, and then you take those particles and you take them apart. If there's 11 subparticles, then you multiply it by 11. Here are 12 molecules. in each molecule, it's composed of many atoms. So you find out how many particles, how many molecules you have, and then multiply it by the number of atoms consisting of each molecule. What is a mole? In the formula of a molecule of carbon dioxide, the subscripts show that carbon dioxide is composed of 3 atoms, 1 carbon atom and 2 oxygen atoms. A mole of carbon dioxide contains Avogadro's number of carbon dioxide molecules, but each molecule contains 3 atoms. Thus, a mole of carbon dioxide contains 3 times Avogadro's number of atoms. A molecule of carbon monoxide, CO, consists of 2 atoms. So, a mole of carbon monoxide contains 2 times Avogadro's number of atoms. So, you'd say a mole contains 6.02 times 10 to the 23rd. So, if you multiply it by 2, that would be 12.04 times 10 to the 23rd. To find the number of atoms in a mole of a compound, you must first determine the number of representative particles. You can use the following conversion factor to convert a number of molecules of a compound to the number of representative particles, molecules or formula units. Representative particles equals moles times the ratio of 6.02 times 10 to the 23rd representative particles over 1 mole. And the next step is to multiply the number of representative particles by the number of atoms in each molecule or formula unit. Remember, sodium chloride, NaCl, is a formula unit. If spread over the entire surface of Earth, Avogadro's number of animal moles, in other words, the little guy that burrows in the ground, would form a layer more than 8 million animal moles thick. What about the length of 6.02 times 10 to the 23rd animal moles? If lined up end to end, 6.02 times 10 to the 23rd animal moles would stretch from the Earth to the nearest star, Alpha Centauri, more than 2 million times. Are you beginning to understand how enormous Avogadro's number is? Now remember, an animal mole is just an animal, a mole of animals, a mole of moles. Perhaps you are wondering just how large a mole is. Well, perhaps not. The SI unit, the mole, is not related to the small burrowing animal of the same name shown in Figure 5. But this little animal can help you appreciate the size of the number 6.02 times 10 to the 23rd. Assume that an average animal mole is 15 centimeters long and 5 centimeters tall and has a mass of 150 grams. Based on this information, the mass of 6.02 times 10 to the 23rd animal moles is 9.03 times 10 to the 22nd kilograms. That means that the mass of Avogadro's number of animal moles is equal to more than 60 times the combined mass of Earth's oceans. An animal mole has a mass of 150 grams. The mass of 6.02 times 10 to the 23rd animal moles is 9.03 times 10 to the 22nd grams. I warn you that these are not necessarily cute creatures. Some of them actually look very alien-like they're from some planet, or they're fake dolls that were created in some wacko's laboratory. But these are really ugly kind of creatures. Look at that bottom middle. That's actually a mole. That's like a nose, but where's the head? Look on the lower right. It doesn't look real. But anyway, these are moles. These are the little guys that burrow in the ground and cause problems to farmers' crops and little victory gardens. That's something that my mother used to say. A victory garden. What's a victory garden? Extra credit, the first person who tells me what a victory garden is. Okay, that's the mole. This guy looks fake, but it's actually quite true. Look at those hands. Look at the claws relative to its body. They're enormous, absolutely enormous, disproportionately enormous. Can you imagine if that mole was 6 feet tall? the mole man, the attack of the mole man. Remember that the atomic mass of an element, the mass of a single atom, is expressed in atomic mass units. The atomic masses are relative values based on the mass of the most common isotope of carbon, which is carbon-12. Table 2 on the next slide shows that an average carbon atom with an atomic mass of 12 AMUs is 12 times heavier than an average hydrogen atom with an atomic mass of 1 AMU. Therefore, 100 carbon atoms are 12 times heavier than 100 hydrogen atoms. In fact, any number of hydrogen atoms is 12 times heavier than the same number of hydrogen atoms. Well, what we're getting to is that hydrogen is going to be used as the template for finding the atomic mass of an element. Here is an example of one carbon atom is 12, 2 is 24, and they're doing it relative to hydrogen atoms. So hydrogen is going to be, everything is based on carbon-12 in terms of masses, everything. And that's an important distinction to understanding much of this chapter. All right, the mass ratio of 12 carbon atoms to one hydrogen atom remains the same no matter what unit is used to express the masses. That's key. So, 12 grams of carbon atoms and 1 gram of hydrogen atoms must contain the same number of atoms. If you look at the atomic masses of the elements in the periodic table, you will notice that they are not whole numbers. For example, the atomic mass of carbon is not exactly 12 times the mass of hydrogen. Recall from chapter 4 that this is because atomic masses are weighted average masses of the isotopes of that element based on percent abundances. So it's an average of all the isotopes. Quantities measured in grams are convenient for working in the laboratory, so chemists have converted the relative scale of masses of the elements in AMU to relative scale of masses in grams. The atomic mass of an element expressed in grams is the mass of a mole of the element. The mass of a mole of an element is its molar mass. For carbon, the molar mass is 12 grams. For atomic hydrogen, the molar mass is 1 gram. Figure 6 on the next slide shows 1 molar mass of mercury, carbon, iron, and sulfur. Compare the molar masses in the figure to the atomic masses in your periodic table, and you will find that they are the same. They are equivalent, not equal. 1 mole of any particle, the mass of 1 mole of any particle is equivalent to the mass of 1 particle in atomic mass units. 1 molar mass of carbon, sulfur, mercury, and iron are shown. Each of the quantities contains 1 mole of the element. How many atoms of each element are shown? Well, if it's 1 mole, it's 6.02 times 10 to the 23rd. 1 mole of particles contains 6.02 times 10 to the 23rd representative particles. That's what a mole means. It's a number. It's a count. Here is the figure. Those just relative amounts. That's a mole of carbon, but not very dense, because look, it looks like the same as iron, but iron is quite a bit more dense, about 4 times more dense than carbon. You also have differences in densities with sulfur. Look at mercury, 200.6 grams, whereas sulfur is only 32.1 grams. So there's major differences in densities. I just wanted you to see what it looked like. Notice that the molar masses were rounded off to one place after the decimal point. All the examples and problems in this text use molar masses that are rounded off in this way. If your teacher uses a different rounding rule for molar masses, your answer to problems may differ slightly from the answers given in the text. What I'd like you to do is use mass numbers, so you're rounding to whole numbers. But if you're using it in a calculation, you may generate a tenth, or a hundredth, depending. But you only want to use 3 significant figures at the most. But I want you to use mass numbers. So you don't, when you're writing the mass number, it's whole numbers. If you were to compare 12 grams of carbon atoms with 16 grams of oxygen atoms, you would find that they contain the same number of atoms. The molar masses of any 2 elements must contain the same number of atoms. How many atoms are contained in the molar mass of an element? You already know. The molar mass of any element contains 1 mole, or 6.02 times 10 to the 23rd atoms of that element. The mole can now be further defined as the amount of substance that contains as many representative particles as the number of atoms in 12 grams of carbon-12. Same thing. You know that 12 grams of molar mass of carbon-12, so 12 grams is 1 mole of carbon. The same relationship applies to hydrogen. 1 gram of hydrogen is 1 mole of hydrogen atoms. Similarly, because 24.3 grams is the molar mass of magnesium, 1 mole of magnesium, or 6.02 times 10 to the 23rd atoms of magnesium, has a mass of 24.3 grams. Molar mass is the mass of 1 mole of atoms of any element. So I read that a little too fast, but it's very simple. However, what we would say is, similarly, because 24 grams is the molar mass of magnesium, we would use that. We would say, we would look at hydrogen, look at sodium, we would say 23 grams. Look at chlorine, we would say 35 grams is 1 mole of just a chlorine atom. To find the mass of a mole of a compound, you must know the formula of the compound. The formula of sulfur trioxide is sulfur trioxide, SO3. A molecule of sulfur trioxide is composed of 1 atom of sulfur and 3 atoms of oxygen. So there it is. So you have 1 sulfur and 3 oxygen atoms. That's what it equals. So you'd find the mass of a sulfur, which is 32. Oxygen is 16. 16 times 3 is 48. So 48 plus 32 is 80. So the mass of 1 sulfur trioxide molecule is 80 AMUs. You can calculate the mass of a molecule of sulfur trioxide by adding the atomic masses of the atoms making up the molecule. From the periodic table, the atomic mass of sulfur is 32 AMUs. That's what I would say. So it's going to be a total of 80 AMUs is that particle. The mass of 3 atoms of oxygen is 3 times the atomic mass of a single oxygen atom. 3 times 16 is 48. So the molecular mass of SO3 is 32 plus 48 equals 80 AMUs. 80.1, I would say 80. 80 AMUs. 80 AMUs. Now substitute the unit grams for atomic mass units to find the molar mass of sulfur trioxide. The molar mass, grams per mole, of any compound is the mass in grams of 1 mole of that compound. Thus, 1 mole of SO3 has a mass of 80.1 grams. This is the mass of 6.02 times 10 to the 23rd molecules of SO3. To calculate the molar mass of a compound, find the number of grams of each element in 1 mole of the compound. Then add the masses of the elements in the compound. And that is the mass in grams of 1 mole of any particle is equivalent to the mass of the total particle in atomic mass units. Finding the molar mass of a compound. The decomposition of hydrogen peroxide, H2O2, provides sufficient energy to launch a rocket. What is the molar mass of hydrogen peroxide? Well, it's going to be H's, 1 each, so that's H2, so that's 2. Oxygen is 32, 16, so 2 times 16 is 32. That'll be 34 grams. Now, this is not fuel for a rocket. They use liquid hydrogen and liquid oxygen to burn. Anyway, what do we know? We know the molecular formula H2O2. We know the molar mass of H is 1 mole of H is 1 gram of H, and 1 mole of oxygen is 16. The answer is the sum of the 2 times the molar mass of hydrogen and oxygen. The answer is expressed to the tens place because the numbers being added are expressed to the tens place. If you express to the ones place, that's fine. It would be 34 grams as we discussed. And there's the math. Convert moles of hydrogen and oxygen to grams of hydrogen and oxygen and add the results. So 2 moles of hydrogen is 2 grams of hydrogen. 2 moles of oxygen is 32 grams of oxygen. 32 plus 2 is 34 grams of H2O2. Remember, the mass in grams of 1 mole of any particle is equivalent to the mass of 1 particle in atomic mass units. How many times will I say it? Many. The answer to the sum of 2 times the molar mass of hydrogen and oxygen. The answer is expressed to the tenths place because the numbers being added are expressed to the tenths place. That's from the book. If you do it to the hundredths place, that's okay. So, if it's 34.0, 34 is just fine. There's no reason why it's not 34, because that's from the table, the periodic table, and that's the mass number, the number of nucleons. This method for calculating molar mass applies to any compound, molecular or ionic. The molar mass of glucose, C6H12O6, is 180 grams, water 18 grams, and para-dichlorobenzene, C6H4Cl2, is 147 grams. In figure 7 on the next slides were obtained in this way. 1 molar mass is shown for each of the 3 molecular compounds. How can you know that each sample contains Avogadro's number of molecules? Well, if it's 1 mole of a substance, the mass in grams of 1 mole of a substance will be equivalent to the mass of 1 particle in AMU. So if I have 1 mole of substances in grams, and that's equivalent to the mass of 1 particle in AMU, then it's Avogadro's number. So that's glucose is 180. On the right, para-dichlorobenzene is 147, and down below, water is 18 grams. So if the mass in grams that you have is equivalent to the mass of 1 particle in atomic mass units, then you have Avogadro's number of particles in that mass. Simple as that. No other consideration. Guess how many jelly beans are in the container and win a prize. You decide to enter the contest and you win. Was it just lucky? Guess? Not exactly. You estimated the length and diameter of the jelly bean to find its total volume. Then you estimated the dimensions of the container to obtain its volume. You did the arithmetic and made your guess. In a similar way, chemists use the relationships between the mole and quantities such as mass, volume, and number of particles to solve chemistry problems. In this section, you will find out how the mole and mass are related. How the mass and mole are related. And here's some pictures of jelly beans. How many jelly beans are in this picture that you can see? Well, I have no idea. And you could estimate how many jelly beans are in each container here. So you could consider the same thing with molecules. In the previous section, you learned that the molar mass of any substance is the mass in grams of 1 mole of that substance, or the mass in grams of 1 mole of any particle is equivalent to the mass of 1 particle in atomic mass units. This definition applies to all substances, elements, molecular compounds, and ionic compounds. In some situations, however, the term molar mass may be unclear. For example, suppose you were asked what the molar mass of oxygen is. How you answer this question depends on what you assume to be the representative particle. If you assume the oxygen in question is molecular oxygen, O2, then the molar mass is 32 grams, 2 times 16 grams. And in this way, you find the mass in grams of 1 mole of the particle. If you assume that that the question is asking for the mass of a mole of oxygen atoms, O, then the answer is 16 grams. You can avoid confusion such as this by using the formula of the substance in this case, O2 or O. Suppose you need 3 moles of sodium chloride, NaCl, for a laboratory experiment. How can you measure this amount? It would be convenient to use a balance to measure the mass or scale, but what mass in grams is 3 moles of sodium chloride? Use the molar mass of an element or compound to convert between the mass of a substance and the moles of the substance. It would be 58 grams. That's what I would use. That's how we would round it. The conversion factor for the calculation is based on the relationship molar mass equals 1 mole. Use the following equation to calculate the mass in grams of a given number of moles. Mass equals number of moles times the quotient mass over 1 mole. The molar mass of sodium chloride is 58.5 grams per mole, so the mass of 3 moles would be 3 times that, which is 175.5 grams. So the mass of 3 moles of sodium chloride is calculated in this way. However, this is the catch. I would say 58 grams per mole. So 3 times 58 is 174 grams because I'm going to use mass numbers. I'm going to say 23 is sodium and 35 is chlorine. Because it's not that, what's important is the process. The answer can be close as long as the process is followed. And that's more significant than measuring something to the 10th or 100th place. When you measure 176 grams, now they're rounding from 175.5 to 176. When you measure 176 grams of sodium chloride on a balance, you are measuring 3 moles of sodium chloride. In sample problem 5, you used a conversion factor based on the molar mass to convert moles to mass. Now suppose that in a laboratory experiment you obtain 10 grams of sodium sulfate, which is Na2SO4. How many moles is this? You can calculate the number of moles using the same relationship you used in sample problem 5. 1 mole equals molar mass. But this time, the conversion factor is inverted. In other words, I'm going to flip it. Because what I'm going to do is I have to find first the molar mass of sodium sulfate, which is 142.1 grams per mole. So the number of moles of sodium sulfate is calculated this way. What conversion factor should you use to convert mass to moles? Well, we just saw it. So use that equation to convert 10 grams of sodium sulfate into moles. So we know that the molar mass of sodium sulfate is 142. So then you do the calculation. Look back at figure 7. Notice that the volumes of 1 mole of different solid and liquid substances are not the same. For example, the volumes of 1 mole of glucose, blood sugar, and 1 mole of paradichlorobenzene, moth crystals, are much larger than the volume of 1 mole of water. What about the volumes of gases? Unlike liquids and solids, the volumes of moles of gases measured under the same conditions, physical conditions, are much more predictable. Why should this be? In 1811, Amedeo Avogadro proposed a groundbreaking expression. So what you would do in the former problem is you'd say 10 divided by the mass in grams of 1 mole of sodium sulfate, and that's the number of moles. These aluminum satellite dishes at the National Radio Astronomy Observatory near Socorro, New Mexico, are naturally protected from corrosion by the formation of a thin film of aluminum oxide, which is Al2O3. And here are the great dinosaurs, not meaning that they're old, just meaning that they're enormous, sitting in the plains of New Mexico. Unbelievably enormous. Used in many films. You can see the little outbuildings and the fences how small they are compared to these utter giants. Absolutely unbelievable. The aluminum satellite dishes in Figure 8 are resistant to corrosion because the aluminum reacts with oxygen in the air to form a coating of aluminum oxide, Al2O3. This tough, resistant coating prevents any further corrosion. What is the mass of 9.4 moles of aluminum oxide? So we're simply going to say, all right, well, aluminum oxide, Al2O3, find the mass of each atom, two aluminum and 3 oxygen, and then find the mass of 1 mole, and then multiply that by 9.45. Here we have the number of moles is 9.45 moles of aluminum oxide. We're looking for the grams of aluminum oxide. The mass of the compound is calculated from the known number of moles of the compound. The desired conversion is moles to mass. So we've got to look up the mass of aluminum and the mass of oxygen. 2 times the aluminum plus 3 times the oxygen is going to be 102 grams. And so you're going to multiply 102 grams by 9.45 moles, and that's going to give you 964 grams of aluminum oxide. It says above, to determine the molar mass of Al2O3, 1 mole aluminum oxide equals 102 grams. Al2O3, multiply the given number of moles by the conversion factor relating moles of aluminum oxide to grams of aluminum oxide. The number of moles of aluminum oxide is approximately 10, and each has a mass of approximately 100 grams. The answer should be about 1,000 grams. The answer has been rounded to the correct number of significant figures. Rust weakens an iron chain. Rust weakens an iron chain. What does that mean? Well, when, as opposed to aluminum oxide, as protecting the aluminum, the formation of iron 3 oxide will weaken iron, weaken the chain, weaken bridges, and it is extremely corrosive, and it just continues to eat away until there's no more iron, there's only iron 3 oxide left. Here's a car that is late for the grave. When iron is exposed to air, it corrodes to form red-brown rust. Rust is iron 3 oxide, Fe2O3. How many moles of iron 3 oxide are contained in 92.2 grams of pure Fe2O3, iron 3 oxide? Well, you find what is the mass of 1 mole of iron 3 oxide. And then you're going to divide 92.2 divided by this number, whatever that may be. So what do we know? We know the mass is 92.2 grams of iron 3 oxide. That's what we want to convert to moles. We want to know the unknown, which is the number of moles. And the unknown number of moles of the compound is calculated from the known mass of a compound. The conversion is mass to moles. So the first thing I've got to do, and you'll understand it directly, is find the mass of 1 mole of Fe2O3. Get it? Okay. It's going to be 159.6. That's the mass of 1 mole of iron 3 oxide. So you actually end up, it says determine the molar mass of iron 3 oxide, 1 mole equals 195.6 iron 3 oxide. Multiply the given mass by the conversion factor relating mass to moles. And you actually, in reality, are dividing 92.2 by 159.6. And then your answer is there. It's going to be somewhere less than 1. It'll be half. Because the given mass, about 90 grams, is slightly larger than the mass of 1/2 mole of iron 3 oxide, about 160 grams, the answer should be slightly larger than 1/2, or 0.5 moles, and it is. So 0.578 moles of the iron 3 oxide is just above 0.5, just above half. So intuitively you would say, well, it's about half, and your answer is 0.578, and that's about perfect. Avogadro's hypothesis states that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. The particles that make up different gases are not the same size, but the particles in all gases are so far apart that a collection of relatively large particles does not require much more space than the same number of relatively small particles. Whether the particles are large or small, large expanses of space exist between individual particles of gas as shown in Figure 9 on the next slide. Figure 9. In each container, the volume occupied by the gas molecules is small compared with the container's volume. So the molecules are not tightly packed. The molecules in this container are small. This container can accommodate the same number of larger particles. So, at standard temperature and pressure, the volume of any gas, of 1 mole of any gas, is 22.4 liters. Go figure. And that's where we're heading for. So if I have large particles that are red, small particles that are blue, they take up the same, if they're both under the same conditions, and they both will have the same volume. So the volume of both gases are exactly the same, regardless as to the size of each molecule. If you buy a party balloon filled with helium and take it home on a cold day, you might notice that the balloon shrinks while it is outside. The volume of a gas varies with a change in temperature. The volume of a gas also varies with a change in pressure. In Figure 10 on the next slide, notice the changes in an empty water bottle when it is in the cabin of an airplane while in flight and after the plane has landed. The trapped air occupies the full volume of the bottle in the cabin where the air pressure is lower than it is on the ground. Figure 10, the volume of gas varies with temperature and pressure. The volume of the gas in the balloon on the left is larger because its temperature is higher. B. The air in the empty water bottle on the left has a larger volume because it is at low pressure. This is the key. Volume is proportional to temperature. Greater the volume, greater the temperature, greater the volume. And pressure and volume are inversely proportionate to one another. So low temperature, high temperature. Low temperature, low volume. High temperature, high volume. Low pressure, high volume. High pressure, low volume. They are inversely proportionate. The rule is that temperature and volume are direct, and pressure and volume are indirect. Pressure and volume are indirect, and that's very important in physics. Now, I just want to take a step back and try to explain to you where a lot of these things come from, because you haven't had physics, and the only thing that might be confusing is the discussion of pressure, which you've had in middle school. But pressure is force per unit area, force per area. So let me explain to you what pressure is, what atmospheric pressure is, and what they're all measured in. So let's first start by saying the acceleration due to gravity is 10 meters per second squared. The acceleration due to gravity is 10 meters per second squared. Okay, that's a constant. So if I'm standing on the ground, I'm accelerating 10 meters per second squared. Regardless of if you're moving or not, that's what you're going to be doing. If you're standing on a floor, you're going to be accelerating 10 meters per second. Okay, now force. Force is mass times the acceleration due to gravity. So my weight on the floor, as I press against the floor standing there, my weight is a force, F sub W. My weight is my mass, which is 100 kilograms, thank God, 100 kilograms times 10, so my force is 1,000, but 1,000 what? See, G is a special kind of acceleration. G is the vertical acceleration, 10 meters per second squared. The vertical free fall weight, vertical acceleration, if I drop something, is G, 10 meters per second squared. So it's going to be my mass, 100 kilograms, times 10 meters per second squared is going to be FW, my weight. Here we go. My mass is 100 kilograms. That is my weight. I'm sorry, my mass. That is going to be my mass, is going to be 100 kilograms. And I'm going to multiply that by 10 meters per second squared, and I'm going to wind up with 1,000 something. 1,000 something. Well, let's see what that something is. What is it that I measure force in? What do I measure my weight in? It's not pounds, it's not kilograms, those are all masses. The SI units for force are kilograms, so I'm going to be mass times acceleration. All right, figure it out. Mass is kilograms times acceleration, meters per second squared. So it's going to be kilogram meters per second squared. Those are going to be the unit labels. Now, what we do, we name something after Isaac Newton, and that is force. So instead of saying kilograms meters per second squared, we say N, or 1 Newton. 1 Newton has the abbreviation N. Kilogram, the abbreviation is kg, and pound, the abbreviation is lb, and meter, the abbreviation is m. Well, the abbreviation for Newton is capital N for Newton. So, kilogram meters per second squared, or Newton. So, the SI units for force are newtons. So now we want to get started and find and just kind of review everything that we've done so far. Okay, this is what we've discussed so far. This is kind of a review. So my weight, FW, equals M times G. Now we're going to take that equation and we're going to find my weight in newtons. So my mass is 100 kilograms. Now, my mass is 100 kilograms. All right. So FW is going to equal the weight. And I know how to do FW. I say 100 kilograms times 10 meters per second squared. And that's going to be 1,000 kilogram meters per second squared. Well, the SI units for force are, wait for it, newtons. kg m over s squared, defined as newtons. So my weight, FW, equals 1,000 newtons. That's my weight, is 1,000 newtons. Now bear with me here. This is a box, a cubic box. That's 1 cubic meter. All right, and you'll see that. Then I'm going to show you what that means. Now I'm going to fill this with water. Now I can put 1,000 liters of water in this box because that's the volume of the box. Okay, that's the volume of the box, is that much water. I can put 1,000 liters, and I'll show you that in class. So it's going to, and that's going to be important. But notice that the bottom of the box has an area of 1 square meter. Okay, so if I can figure out the weight of the box, that weight is a force, and then that's that force per that area. So I've got to figure out what the force is in the box, and then divide it by the area, and that's going to be a pressure. Get it? Good. So it's going to be 1 meter by 1 meter by 1 meter tall. Now, this is what's very significant. As we're finding the volume of this box, it's going to be 1 cubic meter. We can see that. But the surface area underneath the box is going to be sitting on 1 square meter. Do you see that? It's going to be sitting on 1 square meter. A 1 cubic box is going to be sitting on a floor of 1 square meter. So this box can hold 1,000 liters of water. 1 liter equals 1,000 milliliters. The density of water is 1 gram per milliliter. So 1 gram equals 1 milliliter. So 1 liter equals 1 kilogram. So I'm going to be able to put in the box 1,000 liters or 1,000 kilograms. So I can say 1 liter equals 1 kilogram, therefore 1,000 liters equals 1,000 kilograms. This box can hold 1,000 kilograms of water. 1,000 kilograms times the acceleration due to gravity, which is 10, is going to be 10,000 newtons. So 1 box, so it's 10,000 newtons per square meter. Do you get that? 1,000 newtons per square meter. 10,000 newtons per square meter. Okay, so it's going to be 1,000 kilograms times 10 is going to be 10,000 newtons, and it's going to be 1 square meter. 1 cubic meter box has a pressure on the floor of 10,000 newtons per 1 square meter. Now, I'm going to make a stack of boxes, 10 boxes tall, so it'll be 10 meters tall. So what's 10 times 10,000? 100,000. So it's going to be 100,000 newtons per 1 square meter. Do you get that? All right, let's watch this. Watch the show. So I have 10 boxes, and each box is going to be a cubic meter. So I'm going to put a cubic meter next to each box. All right, and so it's going to be 10 cubic meters, because I'm going to have 10 boxes, 10 cubic meters, and then I'm going to have the water in each box will be 10,000 newtons in each box, and that'll be 100,000 newtons, and then the pressure would be force, or the weight, per area, and the area is going to be 1 square meter. So it'll be 100,000 newtons per square meter. Let's see if that's true as we continue through this problem. And this is going to be very significant. The SI accepted value for atmospheric pressure is, they say it's like 101.3 kilopascals, but it's in actuality 100,000 or 100 kilopascals. So the 10 boxes are going to be 100,000 newtons. So it's 100,000 newtons is the force over the area, which is 1 square meter. So 100,000 newtons per square meter. That's going to be the pressure, and that's going to equal, wait for it, standard atmospheric pressure, STP, standard pressure. So it's going to be the standard pressure for 1 atmosphere at sea level is going to be 100,000 newtons per square meter. Pressure equals 1 newton over square meter, and that's a Pascal. That's where you get a Pascal. So STP, standard temperature and pressure, is 0 degrees Celsius and 100,000 pascals, or 100 kilopascals. So that's actually the accepted value, the SI value. It's not 101.3 kilopascals. It's going to be 100 kilopascals. The increase in pressure when the plane lands causes the volume of the air in the bottle to decrease. Because of these variations due to temperature and pressure, the volume of a gas is usually measured at a standard temperature and pressure. Standard temperature and pressure, STP, means a temperature of 0 degrees Celsius and a pressure of 101.3 kilopascals, or as we've seen, it's actually 100 kilopascals now, or 1 atmosphere of pressure. At STP, 1 mole, or 6.02 times 10 to the 23rd representative particles of any gas, occupies a volume of 22.4 liters. Figure 11 on the next slide gives you an idea of the size of 22.4 liters. The quantity 22.4 liters is called the molar volume of a gas. Figure 11, this box with a volume of 22.4 liters, holds 1 mole of a gas. So the following containers will hold 22.4 liters of gas. That's 1 mole will be 22.4 liters of gas, and that's what these containers are going to be showing you the relative value for. These boxes in the lower right are actually bigger than they look. So the little backpack and the funky backpack, those are, and this it looks like a cat carrier and a plastic box. They will hold 22.4 liters of fluid. Sulfur dioxide is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.6 moles sulfur dioxide at STP. And what is shown here are smokestacks. One of the gases may be, I don't know what these smokestacks are from, could be sulfur dioxide. It's also a greenhouse gas and also one of the gases responsible for acid rain. So the knowns are 0.6 moles of SO2. 1 mole of SO2 is 22.4 liters. I want to find the volume in liters of the given amount. Use the relationship 1 mole SO2 equals 22.4 SO2, 22.4 liters of SO2 at STP to write the conversion factor needed to convert the moles to volume. There it is. And we're going to employ it here, 22.4 liters SO2 over 1 mole multiplied by 6.6. Moles cancel, and you're left with 13.4 liters SO2. Again, we continue to look at the smokestacks, which is a result of industry, and deadly gas can cause severe acid rain. And I'll show you some pictures of acid rain here. On the far right, you see forests, trees that are killed by the acid rain, and you have the cycle of acid rain also given here. Because 1 mole of any gas at STP has a volume of 22.4 liters, 0.6 moles should have a volume slightly larger than 1/2 of a mole or 11.2 liters. And in this case, that's true because we measured it to be over 13 liters, which is certainly larger. Fraser firs destroyed on Klingman's Dome by acid rain and insects. Then the insects can come and cause problems because the trees become weaker because of the acid rain. Trees and many other plants are sensitive to aluminum and other metals in groundwater. Acid rain increases the concentration of Al+3 in groundwater, thereby adversely affecting plant growth. Large sections of established forests have been severely damaged. Here is another diagram of the pathways and reactions leading to the formation of acid rain in our atmosphere. This kind of shows the cycle of acid rain and how the different chemicals leach into the environment. The molar mass, the molar volume is used to convert a known number of moles of gas to the volume of gas at STP. The relationship 22.4 liters equals 1 mole of 1 mole at STP provides the conversion factor. Volume of gas equals moles of gas times 22.4 liters over 1 mole. Moles cancel. Suppose you have 0.375 moles of oxygen and want to know what volume the gas will occupy. So it's going to be 0.375 times 22.4. The moles cancel, and you're left with volume of the gas as 8.4 liters. Volume of the gas, 8.4 liters. The opposite conversion from the volume of gas at STP to the number of moles of gas uses the same relationship, 22.4 liters, 1 mole at STP. Suppose in an experiment you collect 0.2 liters of hydrogen gas at STP. You can calculate the number of moles of hydrogen in this way. Moles of gas equals volume of gas times 1 mole over 22.4 liters. Checkpoint. How is the density of a gas usually measured? It's usually measured in grams per liter, believe it or not. Grams per liter is the usual way of measuring the density of a gas. The opposite conversion from volume of a gas at STP to the number of moles of gas uses the same relationship, 22.4 liters equals 1 mole at STP. Suppose in an experiment you collect 0.2 liters of hydrogen gas at STP. You can calculate the number of moles of hydrogen in this way. Moles of gas equals volume of gas times 1 mole over 22.4 liters. Moles of gas 0.2 times 1 mole over 22.4 liters. Moles of gas are going to be 8.93 times 10 to the negative 3 moles of hydrogen. Checkpoint. How is the density of gas usually measured? What is meant by the standard temperature and pressure, which we've already seen? Calculating molar mass from density. A gas-filled balloon will either sink or float in the air depending on whether the density of the balloon's gas is greater or less than the density of the surrounding air. Different gases have different densities. Usually the density of a gas is measured in grams per liter, G per L, and at specified temperatures. So, if you know the how many moles of a gas, so it would be the moles of gas per 1 mole per 22.4 liters, convert the moles to grams, and then you divide by liters. The density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at STP. What is the molar mass of the compound? So, I'm going to set it up. 1.964 grams over liters. And then I've got to separate this as I want to calculate so that the liters cancel. So the density, I know the density of the gas. I know the 1 mole is 22.4 liters. I want to know the gram molecular weight of this. In other words, the mass in grams of 1 mole of any particle is equivalent to the mass of one particle in AMU, and that I use 22.4 liters per mole as my conversion factor, and you see the liters cancel, and you're left with the gram molecular weight. So it's probably, if it's carbon and oxygen, it's probably going to be carbon dioxide, because C is 12, oxygen is 16, 16 plus 16 is 32, 32 plus 12 is 44. So it's probably carbon dioxide, I would say, most likely. Okay. The ratio of the calculated mass, 44 grams, to the volume, 22.4 liters, is about 2, which is close to the known density. The answer should have 3 Simeon figures. 3 Simeon figures is fine. It's actually quite good, but unnecessary as to saying the number, as long as it's not too high, not too low. I would say 3 is high and 2 is low. Anything below or above those values should have some. You should have some real reason why you're doing that. So then, the density of a gas at STP and the molar volume at STP, 22.4 liters per mole, can be used to calculate the molar mass of the gas. Molar mass density at STP times molar volume at STP. Volume of gas, moles of gas, times 22.4 liters over 1 mole. Checkpoint. How is the density of gas usually measured? It's measured in grams per liter, as we've said. That's, I think, the third or fourth time we've said that. You have now examined a mole in terms of particles, mass, and volume of gas at STP. Figure 12 on the next slide summarizes these relationships and illustrates the importance of the mole. The mole is at the center of your chemical calculations. To convert from one unit to another, you must use the mole as an intermediate step. The form of the conversion factor depends on what you know and what you want to calculate. Figure 12. The map shows the conversion factors needed to convert among volume, mass, and number of particles. Interpreting diagrams. How many conversion factors are needed to convert from the mass of a gas to the volume of a gas at STP? So let's look at the map. So the map here is kind of cool. It shows you if you want to convert from, let's say, mass to volume, you've got to go through moles. Mass to representative particles to mass, and then mass to volume. You've got to always go through moles. So know your conversions. 22.4 liters is 1 mole. That's for volume. Molar mass over 1 mole is the mass conversion. And then 1 mole over 6.02 times 10 to the 23rd is for representative particles. Don't forget, you can use the inverse of each of those conversion factors when you're making various conversions. So very cool map. Put this in your notes, memorize it, and then use it. Is your shirt made of 100% cotton or wool, or is it the fabric, a combination of 2 or more fibers? A tag sewn into the seam of the shirt usually tells you what fibers were used to make the cloth and the percent of each. It helps to know the percents of the components in the shirt because they affect how warm it is, whether it will need to be ironed, and how it should be cleaned. In this section, you will learn how the percents of the elements in a compound are important in chemistry. Here's the shirt, and it shows you it's 100% cotton. It tells you how to care for it. Parts of chemistry is simply following directions on a laundry label. Simple as that. If you have had the experience with lawn care, you know that the relative amount or the percent of each nutrient in fertilizer is important. In spring, you may use a fertilizer that has a relatively high percent of nitrogen to green the grasses. In fall, you may want to use a fertilizer with a higher percent of potassium to strengthen the root system. Knowing the relative amount of the components of a mixture or compound is often very, very useful. So what we're going to be doing in this particular subsection is we're going to be looking at percent composition and empirical formula. The relative amounts of the element in a compound are expressed as a percent composition, or the percent by mass of each element in a compound. The percent composition of a compound consists of a percent value for each different element in a compound. So if I need to find the percent element of a compound, I just simply say, what's the total mass of the element, and then divide it by the total mass of the compound. As you can see in figure 13 on the next slide, the percent composition of potassium chromate is potassium 40.3, chromium 26.8, and oxygen 32.9. These percents must total 100%, and they do. The percent mass of element is the mass of the element divided by the mass of the compound times 100%. What we'll see in a few minutes is that you have potassium chromate, and then you also have dichromates. So the dichromates are going to have, for instance, a larger percentage of chromium in them than in the chromate. So they are different chemicals. They are polyatomic ions. Potassium chromate is composed of 40.3% potassium, 26.8% chromium, and 32.9% oxygen. How does this percent composition differ from the percent composition of potassium dichromate, a compound composed of the same 3 elements? We'll see that in a moment. The percent of chromium in potassium dichromate is greater than in potassium chromate. And here's the relationship. For potassium chromate, it's 26.8% chromium and 35.4% chromium in dichromate. The percent by mass of an element in a compound is the number of grams of the element divided by the mass in grams of the compound, multiplied by 100. Now, you can also do it by a chemical formula and using atomic mass units. For instance, if I have sodium chloride, I would say, I know sodium chloride is 58 atomic mass units, so I would say 23 divided by 58 times 100 is the percent of sodium, and 35 divided by 58 is the percent of chlorine, and I can do it that way. If I want to do it using a chemical formula, I can, and using atomic mass units instead of masses from a particular experiment. The imagine you are a chemist who has just finished the synthesis of a new compound. You have purified your product and stored the crystalline solid in a vial. Now you must verify the composition of your new compound and determine its molecular formula. You use analytical procedures to determine the relative masses of each element in the compound and calculate the percent compositions. So, what do you do? How do you proceed? Well, let's do a practice problem. It says when a 13.6 gram sample of a compound containing only magnesium and oxygen is decomposed, 5.3 grams of oxygen is obtained. What is the percent composition of this compound? So what's the percentage of magnesium and what's the percentage of oxygen in that particular compound? Well, what do I know? I know the mass of the compound, 13.6. I know the mass of the oxygen, 5.4. I know the mass of the magnesium, 8.2, all in grams. I want to find the percent composition of magnesium and oxygen, 13.6 total grams minus 5.4 equals 8.2 grams of magnesium. That's how I get the 8.2 grams of magnesium. The percent of mass of the element in the compound is the mass of that element divided by the mass of the compound multiplied by 100. So 8.2 grams divided by 13.6 times 100 is going to be 60.3% for magnesium. Do the same calculation for oxygen, where it's going to be 5.4 grams divided by 13.6 times 100, and that equals 39.7%. So it's 60.3 and 39.7%, and that's going to equal up to 100%, and that would be the evaluation. And that's actually very correct. Percent composition from the chemical formula. You can also calculate the percent composition of a compound if you know only its chemical formula. The subscripts in the chemical formula of a compound are used to calculate the mass of each element in a mole of that compound. The sum of these masses is the molar mass. Using the individual masses of the elements and the molar mass, you can calculate the percent by mass of each element in 1 mole of a compound. You don't have to think of it as a mole. You can just think of it as a particle and use AMUs. It doesn't have to be a whole mole of the substance. It can be one particle. Propane, C3H8, the fuel commonly used in gas grills, is one of the compounds obtained from petroleum. Calculate the percent composition of propane. Again, you could say that C3 is going to be 36 plus 8 is going to be 44. So you could say 36 divided by 44 times 100 and 8 divided by 44 times 100. So we know that the mass of carbon in propane is 36, hydrogen is 8, the molar mass of propane is 44. We want to find the percent carbon, the percent hydrogen, calculate the percent by mass of each element by dividing the mass of that element in 1 mole or 1 particle of the compound by the molar mass of the compound and multiplying by 100. So we've kind of done it already. 36 divided by 44 times 100 is 82%, and 8 divided by 44 times 100 equals 18%. Notice that 82% plus 18% equals 100. It should add up to 100. Now, with round-off error, it could be 99 or 98 or 101, etc., but 100%, or very, very near 100%, is just fine, not a problem. So study that problem. That's going to be one of the problems that are going to be on quizzes and tests for this unit. The percents of elements add up to 100% when the answers are expressed in 2 significant figures. Again, 2 significant figures or 3 significant figures, I'm not going to argue with you. It doesn't matter as long as you follow the process. The answer is just a reflection. Hopefully it's a reflection of the understanding you have for the process. Either that or you got lucky in the process and you made a mistake and you have no idea what you did to get the right answer. Divide the mass of each element by the molar mass and multiply the result by 100. The percent mass is mass of element in 1 mole of the compound divided by the molar mass of the compound times 100%. The percent composition of a compound is always the same as figure 14 on the next slide on the preceding page indicates. Checkpoint. How can you determine the percent by mass of an element in a compound if you know only the compound's formula? How can you determine the percent by mass of an element? Well, you just add up the AMUs of the total compound, and then it's the total mass of the elements divided by the total mass of the compound times 100. Figure 14, the percent composition of water is always the same regardless of the volume of the water sample. A sample of water is always 11.1% hydrogen and 88.9% oxygen by mass. And it's always that. If I do a sample of a thimble of water, what is a thimble of water? If I take 1 ounce of water and do it, or a thimble, it's the same as if I took this entire lake, or possibly the drops on a leaf. I'm going to get the same percentage of hydrogen and oxygen. Parts per million and parts per billion. Percents are used to show relative parts of mixtures as well as the composition of a compound. But when an extremely small amount of a substance is present in a large amount of another substance, it might not be practical to use percentages. Parts per 100 is actually a percentage to show the makeup of the mixture. Instead, concentrations of extremely dilute solutions are sometimes measured in units of parts per million or parts per billion. For example, the composition of a mixture that consists of 1 gram of a substance per 106 grams of water, or 1 milligram of substance per liter of water, can be expressed as 1 part per million. Avogadro's number was not developed by Avogadro in the early 19th century. J. Perrin, a French scientist, first used the term Avogadro's number to describe the number of particles in a mole. Perrin used Brownian motion to determine the number. He used Brownian motion to determine the number. Avogadro, it was just named in honor of Amadeo Avogadro. And here's a beautiful lake with water that has the same percentage of hydrogen and oxygen as if you measured it in a thimble of water. Percent composition as a conversion factor. You can use percent composition to calculate the number of grams of any element and a specific mass of a compound. To do this, multiply the mass of the compound by a conversion factor based on the percent composition of the element in the compound. Suppose you want to know how much carbon and hydrogen are contained in 82 grams of propane. In sample problem 10, you find that propane is 81.8% carbon and 18% hydrogen. That means that in a 100 gram sample of propane, you would have 81.8 grams of carbon and 18 grams of hydrogen. Percent composition as a conversion factor. You can use the ratio to calculate the mass of carbon contained in 82 grams of propane. 82 grams of propane times 81.8 grams of carbon per 100 grams, or 81.8%, equals 67.1 grams of carbon and 15 grams of hydrogen. The sum of the two masses equals 82 grams, the sample size, to two significant figures. How many grams of hydrogen are contained in 100 gram sample of propane? A useful formula for cooking rice is to use 1 cup of rice and 2 cups of water. If a large amount of rice is needed, you could double or triple the amounts, for example, 2 cups of rice and 4 cups of water. The formulas for some compounds also show a basic ratio of elements. Multiplying that ratio by any factor can produce the formulas for other compounds. The percent composition of your newly synthesized compound is the data you need to calculate the basic ratio of the elements contained in the compound. A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of the compound? Well, the first step is going to be changing, basing this on 100 grams, and then saying, well, it's 25.9 grams of nitrogen and 74.1 grams of oxygen, and converting those to moles. So what do we know? We know the percent of nitrogen, the percent of oxygen, they're listed there, 25.9% nitrogen and 74.1% oxygen. We want to know the empirical formula. The percent composition tells us the ratio of the mass of nitrogen atoms to the mass of oxygen atoms in the compound. Change the ratio of masses to the ratio of moles by using conversion factors based on the molar mass of each element. Then reduce this ratio to the lowest whole number ratio. Because percent means parts per hundred, you can assume that 100 grams of the compound contains 25.9 grams of nitrogen and 74.1 grams of oxygen. This is what I was saying. Use these values to convert to moles. So you're going to have 1.85 moles of nitrogen and 4.63 moles of oxygen. So now you want to do the whole number ratio. So you want to divide 4.63 by 1.85. It says the mole ratio of nitrogen to oxygen is nitrogen 1.85 to oxygen 4.63, but formulas must be whole number ratio subscripts. Divide each molar quantity by the smaller number of moles. This gives 1 mole for the element with the small number of moles, and so it's going to be N2O5. The subscripts are whole numbers, and the percent composition of this empirical formula equals the percents given in the original problem. For example, a compound may have the empirical formula of CO2. The empirical formula shows the kinds and lowest relative count of atoms or moles of atoms in molecules or formula units of a compound. Figure 15 on the next slide shows that empirical formulas may be interpreted at the microscopic, atomic, or macroscopic molar levels. An empirical formula may or may not be the same as a molecular formula. For example, the lowest ratio of hydrogen to oxygen in hydrogen peroxide is 1:1. Thus, the empirical formula of hydrogen peroxide is simply HO. Figure 15, a formula can be interpreted on a microscopic level in terms of atoms or on a macroscopic level in terms of moles of atoms. So here I have the microscopic interpretation of carbon dioxide molecule. I can break it down into the number of atoms, the types of bonds. The macroscopic level, 1 mole of carbon dioxide is composed of 6.02 times 10 to the 23rd carbon atoms and 12.04 times 10 to the 23rd oxygen atoms. And that's microscopic and macroscopic. I either look at it in terms of atoms and molecules and bonds or in terms of moles. The actual molecular formula of hydrogen peroxide has twice the number of atoms as the empirical formula. The molecular formula is HO times 2, or H2O2. But notice that the ratio of hydrogen to oxygen is still the same, 1:1. The empirical formula of a compound shows the smallest whole number ratio of the atoms in the compound. The molecular formula tells the actual number of each kind of atom present in a molecule of the compound. For instance, CH is the empirical formula, but benzene might be the substance, and that has a much larger molecular formula as opposed to molecular weight as opposed to the empirical formula weight. For carbon dioxide, the empirical and molecular formulas are the same, and water too, H2O. In the case of carbon dioxide, it's CO2. Figure 16 on the next slide shows two compounds of carbon having the same empirical formula, CH, but different molecular formulas. Aha. Ethylene is C2H2, also called acetylene, is a gas used in welders' torches. Styrene, C8H8, is used in making polystyrene. These two compounds have the same empirical formula. What is the empirical formula of ethylene and styrene? It's CH. Styrene used to make styrofoam. Here's a welder's torch with acetylene, C2H2, a very explosive gas, high energy, can make a very hot flame, used to weld metal pipes or two metal things together because it gets so intensely hot it can melt the metal very easily. And you can see that they need to wear eye protection because of the light is so bright, it's so hot. Styrofoam. Styrofoam is both a convenience and an ecological disaster in the environment because of what it's made from, styrene, and the fact that it's so stable it just won't break down, and it just causes problems in terms of where do you put the garbage? Do you make a Mount Everest type mountain out back somewhere? Not in my town, they say. In using computing formulas, in using percent composition to determine empirical formula, 100 grams of compound is arbitrarily chosen because it is easy to use. If an element comprises 28.5% of the mass of a compound, for example, it makes up 28.5 grams of a 100-gram sample. Any other mass of compound can be used, but computation will be more difficult. So it's oftentimes you just convert the percentages of a particular elemental analysis to grams, and that's based, and you can say that that's based on 100 grams. If any 100-gram sample, 28.5% of that particular compound will be that element. Once you have determined the empirical formula of your newly synthesized compound, you can determine its molecular formula, but you must know the compound's molar mass. A chemist often uses an instrument called a mass spectrometer to determine molar mass. The compound is broken into charged fragments, ions, that travel through a magnetic field. The magnetic field deflects the particles from their straight line paths. The mass of the compound is determined from the amount of deflection experienced by the particles. It's determined from the amount of deflection. From the empirical formula, you can calculate the empirical formula mass, EFM. This is simply the molar mass represented by the empirical formula. For instance, if the empirical formula is CH, the EMF would be 13. Then you can divide the experimentally determined molar mass by the empirical formula mass. So, this gives the number of empirical formula units in a molecule of the compound and is the multiplier to convert the empirical formula to the molecular formula. For example, recall that the empirical formula of hydrogen peroxide is HO. Its empirical formula mass is 17 grams per mole. The molar mass of peroxide, hydrogen peroxide, is 34 grams per mole. So then I say 34 grams per mole divided by 17 grams per mole, and that equals 2. So it's HO multiplied by 2 is H2O2. To obtain the molecular formula of hydrogen peroxide from its empirical formula, multiply the subscripts in the empirical formula by 2. One is understood for hydrogen, one is understood for oxygen. Multiply each one by 2, you get H2O2. How does the molecular formula of a compound relate to the empirical formula? Well, it relates to it by the multiplier. By the multiplier. You have to find the multiplier, which is the molecular weight divided by the empirical formula weight. Look at the compounds listed in figure 3 on the next slide. Ethylene and benzene have the same empirical formula, CH. Methanol, ethanoic acid, and glucose, shown in figure 17 in 2 slides, have the same empirical formula, CH2O. But the compounds in these 2 groups have different molar masses. Their molar masses are simple whole number multiples of the molar masses of the empirical formula, CH and CH2O. The molecular formula of a compound is either the same as its experimentally determined empirical formula, or it is a simple whole number multiple of its empirical formula. The molecular mass, the molar mass divided by the empirical formula mass, is going to be the multiplier. So here I have formula, classification formula, and molar mass. So that's going to be the molar mass of the empirical formula CH is 13. Of benzene, it's going to be 6 times 13, so the multiplier would be 6. So you multiply CH by 6, you get C6H6. Methanol is going to be 30. Glucose is 6 times 30. So you're going to multiply everything by 6. Methanol, formaldehyde, ethanoic acid, acetic acid, and glucose have the same empirical formula. Applying concepts, how could you easily obtain the molar mass of glucose using the molar mass of ethanol? Okay, so what we're going to look at now is we're going to look at methanol, which is a fancy way of saying formaldehyde. It's actually the IUPAC name. And so we have ethanoic acid, we have methanol, and we have glucose. Ethanoic acid is another way of saying acetic acid. So that's acetic acid. The white is hydrogen, the red is oxygen, and the black is carbon. And there's a double bond O. So you see that double bond O, and then the C it's connected to, and then the O, and then the H. That's called a carboxyl group. COOH is a carboxyl group. COOH is a carboxyl group. Finding the molecular formula of a compound. Calculate the molecular formula of a compound whose molar mass is 60 grams per mole, and empirical formula is CH4N. That's dimethylhydrazine. Well, the knowns are the empirical formula CH4N, the molar mass is 60 grams per mole, and the molecular formula is we don't know. So that's going to be ethylene diamine. So we know that the empirical formula is CH4N, and that N represents the multiplier. The EMF is 30. The molar mass is 60, so the multiplier is 2. That equals N. So the molecular formula is you multiply 2 times 1 is 2, 2 times 4 is 8, 2 times 1 is 2. So it's going to be C2H8N2, and that's going to be the answer to the problem. That's going to be the molecular formula. So you have the molecular formula has the molar mass of the compound, ethylene diamine and dimethylhydrazine. That's the chapter. That's chapter 10. Good luck. You're going to need this for the week before winter break. Have a good day. Remember, any homework that's turned in very early will get very much extra credit. So keep that in mind. Have a good day. All the best, and goodbye.